Welcome back to Introduction to Computational Fluid Dynamics, CFD. I'm your professor, Steve Miller. Today we'll be talking about stability and convergence, which are two of the most important aspects of the numerical underlying characteristics of the solver. In the previous class, we talked about two types of algorithms. The first is incompressible and the second is compressible. We won't be looking at the stability of these algorithms explicitly, but they do have complicated analysis which you can look at. In this class, in particular, we'll look at stability analysis, the so-called residual of the L1 and L2 norms, and the convergence. Stability refers to a characteristic of a particular solver numerical method, in that as it progresses towards a solution, if it blows up or if it becomes stable and moves towards a particular solution, which is what is referred to as convergence. If the solver is stable and as it's progressing and it's approaching a particular value and it's well behaved and stable, then we might achieve convergence, which is the property that the solver is not blowing up. We'll look at these in a little bit more detail with some mathematical definitions and examples. Consistency is the idea that a finite difference representation of a partial differential equation is consistent if the difference between the partial differential equation and its discretized form representation will vanish if the mesh is refined. That is, if there's an original PDE and its discretized form, if we solve the discretized form on the mesh and let the mesh spacing go to 0, then we'll obtain, of course, an equivalent solution. This is what it means to have a consistent PDE with the original PDE. This is the property of consistency, and hopefully it's inherent in all our numerical solvers. It can be written in this way mathematically in the first equation on slide 4. We'll let the limit as the mesh size go to 0 of the PDE and say the finite difference approximation be rewritten as, say, the limit of the difference between the PDE and FDE, and it should go to 0. If this is, of course, true, then we would call this consistent. A counterexample would be non-consistency. For example, consider a case where the truncation error might be first order of delta t over delta x. We would let the mesh size go to 0, such as the limit of delta t and delta x, not just spacing, but also time, of delta t over delta x go to 0. This would not be a consistent form of the equations, according to this test. There's also types of equations in differencing using the so-called Dufour-Fraenkel differencing scheme for the wave equation. A stable numerical scheme will be one for which errors from any source are not permitted to grow in the sequence of numerical procedures as the calculation proceeds from one step or iteration to the next. This can be rewritten in this way in the middle pseudo-equation. If errors grow as the solver progresses, the scheme would be considered unstable. If the errors decay, it would be considered stable. It could be that you have a stable solver, but the computational grid will cause it to be unstable. It could be a combination of issues which causes the solver to be stable or unstable. Through best practices, and of course an inherently stable solver to start out with, your code will hopefully be stable. Otherwise, it'll blow up and diverge to very large unphysical values. It has nothing to do truly with consistency. They're two separate topics. A few major points about stability. It is normally thought as being associated with marching problems, but it could be associated with other problems too that are perhaps for steady solutions. Stability requirements are often dictated by the allowable time step size, or CFL number, which we discussed previously. Remember, that's sort of like the speed limit of CFD. If we choose too large of a time step, our solver will be unstable. If we have a time-dependent solution, or CFD solver, then simply lowering the CFL number or time step might give us stability. In many cases, a stability analysis can be performed to define the stability requirements. Unfortunately, for very complicated solvers that are often solving Navier-Stokes equations, this is not possible, but we could always attempt these types of analysis. We'll try some here in this class to try and illustrate the concepts. A further note, which must be made before we continue, is that the so-called round-off error will be the difference between the computer approximation and the actual number. So recall that computers store numbers discretely in a finite number of bits, and that is in the RAM. That means there's only a certain range of the numbers that can be stored, or even a certain precision. If the actual value that we're trying to store has perhaps more decimal places or precision than the computer can hold, it'll simply truncate those values. So there's a so-called thing for round-off error in computers that is really separate from the instability analysis, and this should be accounted for in the schemes. For example, a scheme which is only using, say, real values in the computer for precision of the values versus double precision might be unstable. Increasing the precision can increase stability for some particular problems, especially so when you care about very small quantities relative to very large quantities. We can discuss this more in the one-on-one discussions. Let's next look at some characteristics of stability. The most basic concept, of course, can be illustrated through the so-called heat equation. Let's look at the heat equation here on the first line of the page. Here we've already discretized the equation in an explicit form. It's not implicit, recall, because of course we don't have time levels n plus 1. Just so you recall, here u is the unknown variable, j is the index at a particular grid point, j plus 1 and j minus 1 are in the right and left directions respectively, delta t is the time step, delta x is the grid point spacing, alpha is a constant coefficient, perhaps it's the heat conduction coefficient. And of course, n is the time level. We know the solution at n, and we're trying to march to time n plus 1. We could easily solve this to march to the next solution by solving for u of j of n plus 1. This is what we've done in the second equation on this page. Here we have u of j n plus 1 equals u of j to the n, so this is the solution we know, plus alpha of delta t, which is a time step over the grid point spacing squared, times the numerator of the finite differencing approximation. This is u at the current time step at 3 different grid points, j plus 1, j, and j minus 1. We then can iterate over this equation for every n and advance to large values of n to find the solution. One might ask themselves, if we implement this technique for a particular alpha, delta t, and delta x, will the scheme remain simple or not? This is the question we're asking. But before we continue, let's examine a few other things at a closer look. First, we would examine the exact solution. It would be D. Of course, the heat equation has an analytical solution, which we'll call D. This is the analytical or exact solution. And of course, it could also be obtained numerically if the computer had truly infinite accuracy and we were letting the delta t and delta x become extremely small. That is, the limits. Now we would let the solution by the computer be n. That is the one that we would actually find with a computer with finite precision. So we'll have an analytical solution n, and a solution of the computer we'll call n, the numerical solution. We'll also have a separate analytical solution, which we'll call a. So a computer with infinite precision we'll call solution D, analytical solution A, which is what we've done previously in math classes, and of course the numerical solution, which is what we find with CFD as n. We'll define 2 types of errors. The first is discretization error. That will be nothing but the analytical solution minus the exact solution found with a computer with infinite precision. This is what we'll call discretization error. This is the error due to the discretization of the equations. Discretization error should go to 0 if a minus d is 0, of course, as the limit of delta x and delta t go to 0, which would give us a consistent set of equations. We would also define round-off error, which is the difference between the numerical solution and the solution of the computer with infinite precision. Of course, it's not likely to ever find such a thing, except if you can do it analytically. So there's 2 different types of errors. One is due to the discretization itself. That's done through the approach shown on this page. The round-off error is due to the finite precision of course, the number of bits used to represent numbers for each particular value of u in the computational grid. That's only because of finite precision of the computer. Now, the stability of the numerical method we will examine will be through error growth while computations are being performed. So we can ascertain the particular error of the solution and assess its stability. If error grows and goes to infinity, or very large values, the solver will be deemed unstable. Perhaps the error is increasing locally with iteration. Then it might only be locally unstable, or it could be stable anyway. even if the error is growing, and eventually the solution will become stable and error will decay. These are all types of things you'll see in computational fluid dynamics. Now, we might pose two major questions. How does the error grow overall, and how does perhaps a single error occur for general roundoff? Now, the overall error of the solver can be seen that if there's some strong instability and the error is growing, then it's a global error. If the error is not growing and there's strong stability of the solver, then we would say it's not growing. Now, a single general round-off error might be viewed as a weak type of instability. If they grow, of course, they're unstable. If they're not growing, of course, they're stable. Another point many people discuss, and is frequently answered in many CFD classes, is how is this treated from a practical point of view? And this is where stability analysis comes in. It's very, very difficult to prove a strong global stability of solvers, especially with the complicated discretizations and grids. So we might turn to the idea of weak stability. And weak stability is answered by the so-called Fourier analysis. And it's called Fourier analysis, of course, because it uses the type of basis functions developed by Fourier. It's also called von Neumann analysis after the man who invented it and brought it to the attention of the community. We might ask, is there a type of proof of weak stability that implies strong stability? Let's take a second and appreciate Dr. John von Neumann. You can see three of his pictures on the right. The first one is his Los Alamos badge. He worked on the Manhattan Project and was a key member of it. We recall the Manhattan Project was the secret government project in the United States to develop the nuclear bomb in the World War II. In the upper right is his formal picture. In the lower left is a picture of him in his car. He was an avid automotive enthusiast. He would often buy more than one car a year. They were often Cadillacs, which were seen as the luxury and car to have at the time. There's a whole story behind why he kept buying cars, and I'll let you find that out for yourself. It may not be appropriate for a video. On the lower right, you see, of course, one particular explosion of a nuclear weapon. He was also a major proponent of fusion weapons. He is a big nuclear proponent, and there are many things he did both politically and socially in the United States at the time. His name, of course, later in his life was a household name. Here's a Hungarian American, a true immigrant in the United States, and a story of American dream, perhaps. Technically, he was amazing and considered to be one of the smartest people who lived in the last 120 or 130 years. And certainly he rivaled people like Einstein and his contemporaries in intelligence and creativity. You may not have heard of him too much today because he was spread out in terms of his work, but I've listed just a few things that he was known here on the left for you to consider. For example, quantum mechanics, hydrodynamics, which is really our field, quantum statistical methods, all kinds of areas of mathematics, including geometry, topology, and numerical analysis, which is what we're looking at here. The idea of game theory, which changed economics, and of course, the von Neumann architecture. And if you're watching this video with a computer, then of course, it uses the general von Neumann architecture. So you can thank him for these videos and your cell phones and all the other types of electronic devices that you're using today. That's amazing. Here on the lower left are just a few of his types of accomplishments. Let's look at one more picture just to see who he is. Here's a general picture taken near Princeton of so-called members of the University of Ande's advisory board with the acting president, Lazarna. Now from left to right, you'll see a few particular figures which are listed in the lower part of the caption. In the middle, you can see one of the most famous people which everybody might recognize is, of course, Albert Einstein. On the left, second to the left, there's a picture right here of a little, in the picture, there's a little face right here in the back. That, of course, is John von Neumann. It's actually a rare picture to find him more so in the back. He was someone with a very strong personality, was often out front. Let's now look at what John von Neumann did, or the so-called Fourier analysis or John von Neumann analysis. This is taught in almost all graduate level partial differential equation classes focusing on numerical methods. The von Neumann analysis represents a quantification of the stability of a numerical method applied to some particular discretization scheme for a partial differential equation or set of partial differential equations. The bottom line is if we take a PDE and discretize it and write it as a numerical method that can advance, we should be able to try and assess its stability. Now, we've carefully laid out a few properties. For example, N and D, the numerical solution and the solution of a computer with infinite precision. These are ideas that von Neumann, of course, examined. What is interesting when you look at this approach is think about how it's formulated, and you'll get insight into how a genius thinks. Now, we will define a new variable epsilon, which will represent the error of the numerical solution. That is, of course, the difference between the numerical solution with some epsilon will be the solution with infinite precision. We've written this in this equation in the middle of the page where my cursor is. Now let's return to our best friend, the heat equation. Now, we have previously rewrote an explicit form of the heat equation. Let's look at its original discretization. Here's the left-hand side. This is the partial derivative term operating on u, and the right-hand side is the partial derivative terms operating on u in the x direction. So partial time derivative will be balanced by right-hand side of course, a spatial derivative. This is typical Laplace equation with a unsteady partial on the unknown variable. Now, we have replaced an approximation of u at appropriate values of n plus 1 and n with our definition of the numerical solution, which goes as the solution with a computer of infinite precision plus the error epsilon, the numerical error of the solution. So, for example, a view of j of n plus 1, we've replaced it with d sub j of n plus 1 plus epsilon of j at n plus 1. So here's a view of j n plus 1. You can see that, of course, in the heat equation right here, where my cursor is. Now, let us continue. You'll see that the exact solution of d will satisfy the equation also. Why? Because, of course, if we let epsilon become small, then we will, of course, have an epsilon-free solution. Because the equation is linear, if we eliminate epsilon, d will satisfy the solution. Conversely, if we let d go to 0, epsilon will satisfy the equation. So we can rewrite the original discretization as only one with the error on the equation itself. So here we have, instead of u, we would replace u with epsilon in this particular step. You can see by making this remarkable decision that replacing the equation itself with its particular error, we're able to assess the error in the same physical form as the original form. Now, an exact solution, that is d, and the error epsilon both satisfy the same difference equation. This is a critical and important part of the von Neumann stability analysis. We also have to show that the error will decay and the exact number of solutions both will possess the same growth property in either time or perhaps space. And then we can examine stability. This is a reason why we made this interesting substitution. Also note that we can add in perturbations in the input value for some particular time level n, and they'll either be prevented from growing without bound for a stable solution, or will be growing larger and larger for an unstable solution. For example, if at some time level n, for example 10, I perturb my solution by a value of epsilon. If I then let n grow larger and larger, I'll see that the solution blows up. That would be an unstable case. If I make the same perturbation and the solution decays back to its original form, that without the perturbation would be considered stable. Now, we could consider a distribution of errors instead of one particular error at any particular time level n within the computational domain. So let's rewrite and define our error. At any particular x in time, we'll write our error as some sort of form like this on the right with a summation. M will be perhaps the mode. B will be the amplitude of the mode, and m. I will be the square root of -1, e is Euler's constant, x is the spatial position, and k sub m is the wave number at particular m. Recall, wave number is the number of times an event occurs on a per meter basis. This is a very typical way to write out a Fourier series. Now, we'll examine and define that the number of fundamental frequencies or periods, that is m equals 1, is assumed to be in a domain 2L. So we are now restricting our problem to a domain 2L for the purposes of example. Then we can, of course, rewrite the wave number as km of 2 pi m over 2L. So you can imagine if we set m equals 0, we should get 0. M equals 1 will be 2 pi over 2L. M equals 2 will be 4 pi over 2L, which would be 2 pi over L itself, etc. So this way we can fit in many different sine and cosine waves within the domain over 2L without having any particular problems. Over here you'll see epsilon on the right. For example, this might be how the error changes in that solution based on this decomposition of epsilon. That's fine. You can construct any type of error you wish. Typically, they would have a random phase when you place them in for error analysis. Now, recall that m is the total number of increments within the length L. So if we use a finite approach in a computer, which of course has finite RAM, we have to limit the number of modes. Theoretically, in a von Neumann analysis, we could let m go to infinity. That is, there's no bounds on the number of modes. This is of course not required when trying to reconstruct some kind of function. There's no requirement that it has to go to infinity. Now, we might also examine a single term of the series within our particular error definition. And this is what we've shown in the middle of the page. We might write that the mode m has a particular error epsilon. For example, if we set m equals 2, there's an associated mode epsilon m, which you can see from this equation here by setting m to a particular value and not removing the sum. It would, of course, be equal to the right-hand side of bm e to the I km x. Now we can seek solutions of the form z to the n e to the I km. We seek solutions of this form because of the nature of the stability analysis and equations. Now, for a particular time 0, when n equals n, that is the initial condition, we'll have e to the I km x. Why, of course, because we've set time and mode equal to 0. We'll then let the solution of that particular initial condition be equal to z, which is e to the alpha delta t. Now, based on this, we can write z to the n equals e to the an delta t, which will be e to the at. We can then rewrite this into our particular error at mode m for epsilon. We'll have e to the at, e to the I km x. Here, km is a real quantity, but it could be complex, which would not be uncommon. We then substitute this equation into our relation for epsilon. We will then have e to the a t plus delta t, e to the I km x minus e at, e to the I km x equals this right-hand side involving r, which we'll define as alpha delta t over delta x squared. That should look familiar to you from the original discretization. In fact, when you read out this whole equation, it looks very much like the original discretization. Why? Because here's the time advancement term. Here's the term at the current time level, and the left-hand side would be that original partial derivative discretization with respect to time. The right-hand side, of course, is the spatial discretization. Here's the original term, alpha, which is the heat conductivity coefficient, times delta t over delta x squared. Now, through these substitutions into the original discretized form, you'll see that there's a common factor, and that's e to the at, e to the I km x. Then, if we divide through this above equation, we'll find e to the e to the a delta t is 1 plus 2r, which is alpha delta t over delta x squared, times the cosine of beta minus 1. So we made a bit of a simplification here after this reduction. It's very straightforward. Here, we'll define and compact the term km delta x as beta, and we'll employ the trigonometric identity to find that cosine beta minus 1 here. Here, beta is the wave number times delta x at mode m. Delta x is constant in this scheme, because the grid isn't changing. Now we can employ the trigonometric identity, of course, to try and simplify the right-hand side cosine beta minus 1. We'll have sine squared beta over 2 is 1 minus cosine beta over 2. This is a trig identity, standard from trigonometry. Now we can find, after this substitution, e to the a delta t is 1 minus 4r sine squared beta over 2. We'll find now, through simplification, that e to the j of n plus 1 will be e to the a delta t of e to the jn for each frequency present within the solution. you'll see that it's now clear that if the magnitude of e to the a delta t is less than or equal to 1, then a general component of the error will not grow. Let's look at that from this particular equation. If we take the magnitude of e to the a delta t, if it's greater than 1, then of course this is not growing. We'll try and put this in a simpler form. What does this mean? It means that if the magnitude of e to the a delta t is less than or equal to 1, then the general component there will not grow from any one particular time step. So the stability of the scheme depends on particular values of this magnitude at any particular time step. This can be written in a different way. If, of course, this can be written in a different way. We might look at it as the magnitude of 1 minus 4r sine squared beta over 2. That should be less than 1. If this is true, of course, then we would have a stable scheme. We call this stability analysis and requirement the so-called amplification factor. Why? Because it's related to how the solution is being amplified as we advance to the next time level of n plus 1. Often in more complicated schemes, we might just call this g. It might be represented another way, of e to the j of n plus 1 over e to the j n. We should consider two particular cases for the equation we developed on the previous slide for the right-hand side, 1 minus 4r sine squared beta over 2. For example, we might suppose that 1 minus 4r of sine squared beta over 2 is greater or equal to 0. Then you can rewrite it as 4r sine squared beta over 2 is greater than or equal to 0. We might also write that 1 minus 4r sine squared beta over 2 is less than 0. Not less than or equal to, but less than. Then 4r sine squared beta over 2 minus 1 will be less than or equal to 1. You'll see that the first condition is always satisfied for r is greater than or equal to 0. And the second inequality is only satisfied for r is less than a half. This is the so-called stability requirement of this particular method. We have put bounds on r, that it must be always greater than or equal to 0, and it is always less than a half. This means that there's numerical restrictions on the time step relative to the mesh space. For example, for this range of r values, and recall that we define r as alpha delta t over delta x squared. Now alpha is always some positive constant coefficient for the heat conduction equation. Delta x is likely constant for the particular grid. What we control as a user and someone finding the solution is usually delta t, the time step size. That's a step which we advance in time. If we set delta t to be too large, r will be too large. It'll be larger than 1/2. If we set it to 0, of course we won't advance in time at all, and we'll just find the next time level is equal to the current, because we're not advancing in time at any one particular level. Finally, we would have to set delta t to be some value between the values of r and less than 1/2 and r greater than 0. By doing that, we can ensure that our scheme is stable for a given delta x and coefficient alpha. Let's look at a particular example to solidify this. And you'll also be asked to do a basic von Neumann analysis on a particular homework problem for a different linear partial differential equation. You'll see that doing it once and following the steps on these slides next to each other, that is fairly straightforward. We might ask, what is the stability requirement for the 2D heat equation using a simple explicit scheme? Previously, we did the one-dimensional example. Let's walk through it together, and I think these steps will be much more clear. First, we have to represent our original linear continuum PDE of the unsteady heat equation in 2 dimensions with constant alpha and its finite difference form. You'll notice we ask for an explicit scheme here, so we write it in an explicit form. Now we have 2 subscripts, j and k, for the x and y direction, respectively, x, y. We have time level n plus 1. The left-hand side has been discretized with explicit Euler scheme. So that's u of n plus 1 at jk minus u of n at jk all over delta t. That's what we put on the left-hand side. The right-hand side, we put in 2 central second-order differences for the second order partial derivatives of u with respect to x and u with respect to y. We then solve this equation in discretized form in its explicit form for u of jk at time level n plus 1. Of course, it's equal to the original solution plus r, x, and r, y. So instead, now we're in 2 dimensions, we actually have 2 particular values coefficients r. The first r sub x, and this is not partial r partial x, it just means sub x, that is the r coefficient with respect to partial 2u partial x squared will be alpha delta t over delta x squared. Similarly, r sub y will be alpha delta t over delta y squared. Now you'll see that the Fourier components will take, based on our knowledge of PDE, and this is our choice based on our knowledge of the analytical solution of this PDE, we'll write those Fourier components, which can be used to find analytical solutions, as something like u of j to k, that's u at some particular grid point at time level n, will go as e to the at times e to the ikx x, e to the ikyy. So now we have two wave numbers, kx and ky. A is a coefficient. That's something to do with the growth with respect to time. Now, we will define two variables, beta 1 and beta 2. We'll let beta 1 be the wave number in the x direction times the grid point spacing in the x direction, and beta 2, the grid point spacing in the y direction times the wave number in the y direction. Upon substituting of these particular forms of beta 1 and beta 2 and simplifying, we'll find an equation for e to the a delta t will be 1 plus 2rx of cosine beta 1 minus 1 plus 2yr of cosine beta 2 minus 1. So we take this definition of e to the a delta t, like in the previous equation here, and make our substitution, and using our identity to simplify it. Here we have sine squared beta over 2 is 1 minus cosine beta over 2. This should look very familiar to previous identity used in the one-dimensional case, except now we're in 2 dimensions. We can see now, through following the same approach as shown previously, that the amplification factor for stability will be 1 minus 4rx of sine squared beta minus beta 1 over 2 minus 4ry sine squared beta 2 over 2 will be less than 1. This is really the amplification factor g. Now, this inequality must be true for the scheme to be stable. If this amplification factor or growth factor is greater than 1, of course, the solution will grow with time, no matter what we do, and it'll blow up. So we might have discretized the equations and programmed them correctly and chose a well-behaved initial condition, but this explicit Euler scheme to march in time will always be unstable. This inequality will be true if and only if, and we've just expanded out and trying to simplify it for analysis, as 4rx of sine squared beta 1 over 2 plus 4y sine squared beta over 2 will be less than or equal to 2. Try and do this operation yourself. You'll see that the stability requirement, the ranges of this particular inequality, to be less than or equal to 2 will be in a range, and it'll be rx plus ry must be less than or equal to 1/2, or alpha delta t of 1 over delta x squared plus 1 over delta y squared will be less than 1/2. So these conditions must, of course, be true for the scheme to be stable. The stable requirement is more restrictive in 2 dimensions, and it's even more restrictive in 3 spatial dimensions. So even though we're using the same discretization and time marching scheme, it changes, the stability requirements change in multiple dimensions. Now in practice, we often use numerical methods to find stability itself. Because our equations we're working with are not linear, we do not have the luxury of performing this so-called von Neumann stability analysis for a complicated discretization and nonlinear partial differential equations. But you can see we can also find numerically the stability amplification factors for a particular scheme and grid. You might ask yourself, well, that's all well and good, but how do we find the stability analysis for a system of equations like Navier-Stokes? Let's look at this a little bit more detail. For example, we might write our equations as partial e partial t plus partial f partial x. So we have our time field variables e, and we're advancing them in time, and they're balanced of our right-hand side. We have chose this simplification of the Navier-Stokes equations in 1 dimension because, of course, it mimics the type of PDEs we did analysis for just now. That is, there's a time derivative, and of course there's a spatial derivative. Let's now try and examine our nonlinear equations, but of course our stability analysis is linear. Let's do this anyway. We'll rewrite our system this way. Partial e partial t plus partial f partial e partial x. Of course, we retain our same system of equations through a linearization of partial f partial e. We can rewrite partial f partial e as a coefficient matrix A, which is the size, or order that is, of the number of equations. For Navier-Stokes, it might be 5. That is, it's a 5 by 5 matrix, holding coefficients. Now, We will call A the Jacobian matrix because it's partial f, partial e. It is a difference because, of course, of the two vectors e and f. It's not really like the coordinate transform we talked about earlier, but it is like this Jacobian matrix because it's like the difference between the two cases in a linear sense. Now, we locally linearize the system by holding A constant. That is, we're going to fix A at some particular solution time and space. Now we'll let E advance through a single time step. So we're not doing this for all time step. We're fixing the coefficients A. We're holding it constant and only performing a single time step. So this whole analysis and stability requirement would change as the solution advances. An example, we might discretize and write e of the j n plus 1 equals this right-hand side, where we have an explicit scheme at time level n. So everything on the right-hand side is known at time level n. I, of course, is just an identity matrix, A are coefficients, and we have delta t over delta x, because we've just used explicit Euler, which is probably not the most stable numerical scheme. But let's do it just to see what happens. Now, we'll apply a typical form of the Fourier series to this particular discrete difference equation. So this is an assumption that, of course, the solution can be rewritten as a Fourier series. This might be very difficult for some cases, but it'll work for many. We can then rewrite our equations as e to the n plus 1 at wave number k goes as the amplification matrix with delta t and wave number k at the current solution time e to the n. Here, we define the amplification matrix as G goes as the identity matrix times cosine of beta minus I delta t over delta x matrix A of sine beta. Here, we will define and let e to the n represent the Fourier coefficients in a typical term. This is exactly like what we did before. Now, we'll call that matrix G the amplification matrix. Now, as you can imagine, some particular statistics of G will dictate if the scheme is stable or not, because that is actually the amplification matrix. If it's a scalar and it's less than 1, the scheme is likely stable for this linear set of equations. But it is not a proof, it's just likely stable. It'll be dependent on the wave number and frequency decomposition of the solution at that particular time, step, and size only. The largest eigenvalue of G, therefore, must obey for stability purposes that the largest eigenvalue of G, if we find the eigenvalues and find their magnitudes, it must be less than 1. So we might have multiple eigenvalues. If any eigenvalue in its magnitude is greater than 1, the scheme will be unstable for that particular point in time and space. This will imply, through this substitution, that the maximum eigenvalue of A will be delta x over delta t. It'll be less than 1. This analysis does not necessarily include the effects of the boundary conditions, and so an entirely different analysis of the boundary conditions must be made for stability. This is often a topic, and many boundary condition choices for some solvers might cause the solver to be unstable, where the solver itself is inherently stable in the middle of the domain. Remember, the boundary conditions are actually a set of different partial differential equations, or simplification of them, or even specification of the solution on the boundary with its respective discretization. We would also have to apply some sort of stability analysis to the boundary condition equations, separately from the stability analysis of the numerical scheme that advances it in time within the middle of the domain. Now, we showed that the stability of a finite difference operator will be related to the amplification matrix. Therefore, we can rewrite this equation here in the upper left with the new definition of G, and we'll have e to the n plus 1 of wave number will go as G, which is a function of delta t and wave number, which is spatial, at time level n times e perhaps to the 1 of k. Now, the stability condition here requires that some positive time tau and the matrices will be formed uniformly and bounded between some time 0 delta t and tau and 0 of n delta t and capital T. Here tau is one particular short time and t might be the number of time steps n. Now, for all wave numbers where t is the maximum time in our solution, we might view this as a type of von Neumann analysis, and we'll find a necessary condition for stability. Necessary condition means it is not sufficient to guarantee stability. It is just a necessary condition. If we don't meet this linear stability analysis condition, then the scheme will absolutely be unstable. If we do meet it, it might be stable or it might be unstable. It's a necessary but not sufficient condition. Now, for each eigenvalue and wave number, where sigma I represents the eigenvalues of g of delta tk. So this is what the sigma represents. It's the eigenvalues of our amplification matrix, which are, of course, defined based on the linearization of the coefficients a at some particular time step. So, of course, at one time in your solution, this might condition be met, and other times it will fail and your scheme will become unstable. This is often seen in CFD, especially for time-dependent problems. This is one of the most classical examples which illustrates the idea of course, the stability of a more complicated set of nonlinear equations and the relation to a linear set of PDEs like the heat equation, Laplace equation, or wave equation. Let's look at another example for stability analysis using the so-called Fourier or von Neumann analysis. Here's our example from the book of Chung. Let us try and determine the stability requirements necessary for solving the system of first-order equations. Here they are. They're very simple and just used for illustrative purposes. The first one is partial u partial t plus c partial v partial x, which is 0. And the second is partial v partial t plus c partial u partial x, which is 0. So you can see we have two unknown variables, u and v, and they're dependent on time and one spatial direction, x. So it's a space-time set of linked partial differential equations. And we want to solve this using the so-called lax method. This is a type of numerical scheme to solve the equations of motion. Now, let's just concisely follow the previous steps to solidify them in your mind. First, in this problem, we'll set a solution vector E as u and v. Why? Because the unknown variables are u and v. Look at the time derivative operator, u, v. We set our solution vector. Now we can rewrite this two linear partial differential equations in a vector form. We'll write it as partial e partial t plus the matrix A partial e partial x is 0. What we haven't done is found the matrix A. Of course, it can be found simply by looking at the coefficients of the system of equations. We can see clearly that A should be 0c and c 0, where c is a constant coefficient. You can multiply through vectors by holding u constant for the first equation, and you'll arrive at the first original equation, and v for e in the second equation, multiplying through by a of c0 partial e partial x. And you'll, of course, arrive at the second equation. So we've now taken a linear set of partial differential equations and put them in the exact form that we shown earlier. Now, we don't have to do any more work that's very difficult because we've already showed that the stability properties of this particular equation only depend on the coefficients A. If the system of equations were nonlinear, we would choose a particular point in space-time and linearize A. Here, since we're already dealing with a linear set of equations, A is already linearized. You can see there's nothing to non-linearize. It is a linear constant coefficient equation already. It's all constant coefficients, so there's no work that must be done. Now, all we have to do is find the maximum eigenvalue of A. If you look at the eigenvalues of the matrix A and review a linear algebra book, if you forgot how, the largest eigenvalue you'll find will be C. Therefore, the stability requirement will be the usual CFL condition, which is fascinating. That is, the largest value of C will be the dictate CFL number. We take this eigenvalue multiplied by delta t over delta x, and we'll see its magnitude must be less than 1. This is following exactly the same approach in the previous slides. Here, lambda max, which is in this case c, will be delta t over delta x. Its magnitude must be less than 1. What does this mean in practice? If we solve this system of equations using the so-called lax method, which is to do with its discretization and time marching technique, we'll see that we have some particular grid. Perhaps that grid has a constant spacing delta x. There's also a coefficient c, which is the largest eigenvalue, but this just corresponds to the coefficient c in the equations of motion here. What we can choose now is delta t. If delta, say for example, c is 1, and delta t is 2, and delta x is 1, that would mean that we have a CFL number of 2. It would be unstable because it's greater than 1. If c is 1, delta x is 1, and delta t is, say, 0.25, take its magnitude, then of course we have 0.25 and the scheme is stable. Here, we can always calculate the CFL number of the scheme. You see in this case, CFL number of less than or equal to 1 will be stable. If we choose a CFL number greater than 1, it will be unstable. Another way to look at this is, say we're given some c, which is some perhaps very large value, and we have already made a grid. We would have to look at c, take c, divide it by delta x, and of course make sure that we choose a delta t which is as close to 1 as possible but less than 1. This way we can ensure numerical stability of our scheme and advance in time as fast as possible. This is one example of using a CFL number to make the most computationally efficient scheme to advance in time, using, of course, the lax method for these particular variables. You'll see that there's different stability requirements for different types of numerical schemes. For example, the classic Runge-Kutta scheme has a maximum CFL number for stability of approximately 1.5. There's many other types of schemes. And of course, this type of stability analysis can also be applied to implicit schemes. And it can be shown using the same type of analysis for linear equations that they are unconditionally stable. They're always stable. Let's now turn our attention to the so-called residual and the L1 and L2 norms. This is the idea of how we're assessing error as solvers progress. If we have a CFL number and it is stable, and we have a scheme which is consistent, then we can start looking at residuals as the solver runs. In practice in CFD, when your solver is running, you can monitor the residual. What is the residual? It's basically an error within the result at any particular time. That is, if we look at the LTE or residual, we can monitor it. If it's large, of course, there's a large error within the equations. If it's very small, then of course there's a very small error. How do we find residual? There's many different ways, and we'll give some examples. And there's two types that we're most interested in CFD. Residual might be written as the so-called L1 or L2 norm. Now, the error of the result is the residual. If we take an equation and set the right-hand side to 0 and evaluate the left with the computer, and it's not equal to 0, then that is the so-called residual. It is the error of the equation. Now, a most simple example of residual we've shown on this particular page. For example, we have a function of x, and it'll be equal to a constant b. Now, we can put b and f on the right-hand side and set it to 0, of course. Then we'll have b minus f at some particular value of x naught. The residual at x naught will be given as the error exactly at x naught. So you might say, well, if I evaluate b and f, I should always get 0, and my residual will be 0. That would absolutely be true if you have the true analytical solution. In a computer, recall there's multiple kinds of error. For example, truncation error and discretization error. So it's very unrealistic to expect that b minus f will ever be exactly 0. If we take the magnitude of the residual, it'll usually be positive. We'll talk about some examples of this in best practices in a few minutes. If we do not know a particular value of x, then we can still find the residual, which is exactly what we do in CFD. The exact value of x, perhaps, is something that we would do with x naught in an analytical solution. This is not particularly done in CFD because, of course, we don't know the analytical solution. There's two types of ways to measure a residual. Usually, we look at it in terms of its magnitude, which is the L1 residual. The L1 residual, or norm, is nothing but the sum over all the values of the magnitude of xr, which of course is a vector of the residuals. So at every grid point in the solution, I would find the residual, and I would sum them up and take the magnitude. That's the L1 norm. It's the total residual within the whole computational domain. In CFD, errors are typically represented by the so-called L2 norm. That will be written as, in a very similar way as the L1 norm, but with a square root. We are essentially summing up the RMS residual in the whole domain. RMS is root mean square. Here, xk is still a vector of the residuals. We're just summing over k versus r for these two cases. Your CFD solver, as it goes from one iteration to the next in a steady or unsteady solution, can report the residual. In steady solvers, you want the residual to go down. A small residual is good. It means with time, or iteration of course, it shows that your solver is stable and is converging to a solution. Eventually you would expect your L2 norm of the residual to go to a very small value and stop changing. This means that your solver is completed and it's not improving the numerical solution at all. Now that we define mathematically what the residual is in the solver, and it's important that you understand this and remember the definitions of residual. Remember, residual is the error in the solution. If that's the most basic thing you take away, mathematically it is the RMS error at a particular iteration or with time. You want your residual to go to 0. Now that we've talked about consistency and stability, remember the summation of the two implies convergence. Let's return to this topic, which we introduced in one of the first classes. Convergence is where a solution of the discretized forms of the equations will or should approach that of the governing PDE as the mesh is refined. This is convergence. Now, for linear equations, that is, not the Navier-Stokes, which are nonlinear, there will be a mathematical theory which proves the numerical solution of the discretized equations as a solution of the original PDE. Now, there's a so-called Lax equivalence theorem. The Lax equivalence theorem states that for a properly posed problem with consistent finite difference representation, stability is the necessary and sufficient condition for convergence. If you find this statement confusing, you just might write it as a pseudo-equation. If you have consistency, and you have stability, then you have convergence. This is the Lax equivalence theorem written in a very simple way. Remember what consistency is. That's your discretized equations, continuum equations as delta t and delta x go to 0. Stability is the property of the solver, which we have illustrated through the von Neumann analysis. That is, as we march in time towards a solution, this solution does not blow up. If we have these two properties, then we have convergence of our scheme. And of course, with time marching or iterations of the solver, we will and be guaranteed, of course, to go towards a solution. Now, depending on how you set up the problem, you may not have stability. The grid itself may not let you have consistency. This is the importance of having an excellent computational grid and choosing the right numerical scheme and meeting, of course, the requirements of CFL number. If you do these two steps correctly, then of course you're guaranteed convergence. In practice, it's very hard to guarantee and know in any possible way that you have stability and convergence or consistency. And the only way to find out in practice is actually to run the solver and solve the equations. Remember, in CFD and in general, convergence is very difficult to prove for a particular set of equations and discretizations. Now, we will show that convergence is shown through multiple numerous numerical methods and multiple CFD runs. We'll do this in class, and you'll see as you change particular numerical schemes, your solver will diverge, and it'll be very frustrating because you may not know what's causing the divergence. It could be that you have a poor computational grid, which ruins consistency. It could be that you have a boundary condition with a particular flow that causes the solver to be unstable. It could be that you just chose a CFL number which is too large. Perhaps you've chosen a numerical scheme which is not stable, even though if it's implicit for a particular set of boundary conditions and initial condition. These are all possibilities, and it's going to be very frustrating. But this is part of what CFD is. It's going to be setting up cases and trying them out to see if you can achieve convergence. Now, when advancing in time or solving a steady problem with an iterative algorithm, you might ask, when should I stop? I can monitor the residual, as you'll see in your CFD solvers, but how do I know when to stop? Well, the most easy way is to examine the change of the solution between iterations. This may not be the best method, but it's one technique. For example, if I'm plotting the residual of the equations with iteration for a steady flow, it should eventually become very, very small and a constant value, typically anywhere from 5 to 6 order of magnitude reductions of the residual is appropriate for a typical steady run. You should then, of course, also look at the solution itself and inspect it and make sure it makes physical sense. You should also look at and apply grid-independent study. All these things should be done before you say, I have a converged solution which is physically correct. You can, of course, overcome some of these problems by answering this equation a little bit different way, by normalizing the change in residual through a pre-selected amount. For example, let's propose the following. We'll say delta to the n equals phi to the n plus 1 minus phi to the n. That will go as something like lambda 1 minus 1 of lambda 1 to the n of a1 phi 1. Here, we'll define delta n as the difference between the solution iteration n plus 1 and n, and lambda is the larger eigenvalue or spectral radius of the iterative matrix if we're doing a linear problem. Then we can estimate the eigenvalues of this particular system as lambda 1, where the lambda 1 is the eigenvalue. It'll be, of course, the magnitude of delta n over delta n minus 1. You can see that by definition, lambda 1 should be less than 1 if the scheme is stable. Here, A will be the L2 norm, which we just defined. Now, this is very theoretical, and in practice, what you can take away in a CFD solver that's solving a nonlinear set of equations is that over time, not locally from one iteration to the next, but maybe over thousands or tens of thousands of iterations, your residual should keep decreasing. If we can estimate that eigenvalue, and is easy to estimate for an iterative solver that's linear, we can go through and rearrange our delta n equation in this form. This might yield another estimate for the iteration error, that is the error between each particular iteration. And of course, this goes as the norm of delta n over the eigenvalue minus 1. This approach is only for linear systems and requires at least 2 time levels of iteration. You can explicitly calculate these quantities, for example, the heat equation, which we showed in this class, if you iterate from one solution time to the next, n to n plus 1. It can be applied to nonlinear systems as well, especially near convergence, but it's not typically done in practice. It's here to illustrate some mathematical points for you. Now, this is based on real eigenvalues, but with real systems of PDEs, of course, you might have complex eigenvalues. A complex form of this representation is shown here on the bottom of the page. You can see how it's very much different than the one previously defined at the top of the page. We can also subtract now 2 successive iterations to obtain some delta to the n, and we might call this omega as lambda 1 minus 1 a1 of phi 1. Then we would obtain delta n goes as lambda 1 n omega plus lambda 1 complex conjugate n of omega complex conjugate. Now, as the magnitude of the eigenvalue lambda 1 is the quantity of the greatest interest, we can write lambda 1 as L e to the I theta. And you can show through a similar analysis for z to the n, you have this equation, where of course L is the square root of z to the n over z to the n minus 1. Here, L will be the estimate, not the actual, but the estimate of the greatest magnitude of eigenvalue. You'll see that complex eigenvalues cause the error to oscillate, and shape of the error will be dependent on the iteration number even for large n. You might wonder why in introductory CFD class I've shown you this complex error analysis. For now, it's not important that you know every particular detail, but what you'll see in your CFD solvers that are solving the Navier-Stokes equations and their variants is that, of course, you'll see oscillations in the residual. When you see oscillations of the residual, you'll know that you have complex eigenvalues in your particular system at that particular iteration or time. And that's very interesting, and it's an explanation for a phenomena that many students ask about. Many students want their residuals to become very, very small and not change. But in practice, a lot of times you'll see oscillations, very much like a sine wave or some more complicated function near the end or converged solution. This doesn't mean the solution is not converged, it just means that your eigenvalues, of course, are complex. This is troubling at first, but of course, like many things in mathematics, you get used to it. Now, for most CFD problems we look at, we can approximate the relationships between epsilon, delta, and L. And we've done this through this equation here. But of course, it's only an approximation. It is not good practice to estimate these types of things on a per iteration basis, but is a very good estimate on an average basis through the iterations of a steady solver. Now, typically the running averages in iterations might range from 10 to 100 and depend on the problem. This will all be done for you by a CFD solver automatically. There's almost no steady CFD solver that does not calculate residuals for the estimation of convergence. That's how important they are. And they're available in all commercial solvers and research solvers. Only very few solvers that are being newly developed won't have these types of criteria. Now, remember, in practice, we do not know the largest eigenvalue, and we do not know if it's real or complex. But you can probably guess if it's real or complex, depending on the oscillations near the, of course, converged state. So we need more general methods. We might guess that if the eigenvalue is real, and if it has the following ratio is small, say r is about 1 and x minus 2, then we can rewrite r in this form as d to the n over delta n squared. This will be complex if, for large r, for example, and it will be based on this estimate. We can choose the appropriate way to quantify the error and therefore the convergence of the scheme. Let's now summarize and talk about major points of the ideas of convergence. In practice, those who run CFD codes for production use are not estimating these values. It's done automatically by the solver. Now, the reduction of the residual of the simulation is one excellent, but not the only criteria to know if the simulation is converged. You can say my solution is converged if you inspect a residual versus all iterations and it's become many orders of magnitude smaller than the initial residual or L2 norm. That is, the error has decreased to a very small value. You can choose when to stop iteration. Only the user can. There could be numerical tests to do this for you. However, I think it's better to set a large iteration value and look at the L2 norm or residuals with iteration. The iteration will stop, or the user can stop it, when the residual norm has been reduced to some fraction of its original size. For example, at iteration 1 of the solver, if my residual is, say, 1, I would expect my residual to go down at least 3 or 4 orders of magnitude or more. Now remember, you have a residual for each equation that you're solving. You would have one for densities, momentum equations, energies, and turbulence models, for example. You would want all these to go down by at least 3 or 4 or perhaps 10 orders of magnitude to have a converged solution. So some cases will not have multiple orders of magnitude reduction. Those should be a little bit suspect and treated suspiciously. It could be the case where your residual increases, especially when you have an ill-posed initial condition. This is more the user's fault for not specifying an appropriate initial condition for the equations of motion. We can also examine the error and residual reduction with inner iterations as well as outer iterations. Please recall our numerical class where we discussed the idea of inner iterations versus outer iterations. Typically, outer iterations were being used to accelerate and find more accurate solutions. Typically, we'll stop the inner loops after a few reductions of a residual error. That is, we are applying and examining residuals not only on perhaps the iteration, but also the loops that go around and try and reduce the error between particular iterations and time steps. We would never stop an outer iteration before the residual is multiple orders of magnitude. And this could be measured for all the field variables as I just mentioned, for densities, velocities, pressures, and temperatures, etc. Now, we'll define that the sum, or the absolute residual, will be the L1 norm, as we showed mathematically. It can be used instead of the root mean square, but it's much more typical that you would see the RMS residual, that is the L2 norm versus the L1 norm. Why? Is of course it keeps it dimensionally correct in the equations of motion. And I think the L2 norm, or mean square residual, is much more physical to examine than, say, the absolute error. Now, one main important point, and I put it in orange. Let's read it together. By examining the reduction of residual in both the inner and outer loops, and by examining the solution through visualization techniques, we can claim that the solution is converged. You'll have to do all these things if you want to claim, say, in a report, presentation, or paper, or analysis on CFD that you do have a converged solution. If you can't do these things and do grid independent studies, then you cannot say that your solution, the numerical solution, matches the equations of motion, and you're not going to be able to do any analysis with the results. You'll have to go back and redo the whole thing. Let's now look at some examples of residual and error with respect to iteration. Now, we'll look at this example with a particular equation, which is, of course, the Laplace equation. And we'll look at the Laplace equation in a square domain. And our solver will use the so-called successive over-relaxation technique. We'll note that when a complex eigenvalues are present, that we'll have oscillations in the system. That is, it's non-monatomic, and that is the reduction of the error has oscillations. We see the non-monatomic reduction of residual with iteration as something that's very typical in CFD. For Laplace equations, it's very untypical because, of course, it has real eigenvalues in the analysis. Let's look at the case on the right to illustrate this. On both of the x-axis, we have the iteration. That is, the solution starts at iteration 0, and the solver iterates from, say, 1, 2, 3, 4, all the way to 150 in both cases. The y-axis is the residual. In this case, it's written error, and it's on a logarithmic scale. Now, let's look at the left figure. For these particular residuals, and what they are for the moment, their breakdown isn't that important, we see that we have particular lines. All these lines are decreasing at what looks like a linear form. But remember, this is a log linear plot. The y-axis is log of error. So we can see that with iteration count, our residuals are all decreasing. They all started around 10 or 20 in this type of range. At only 125 iterations perhaps, they've gone down to 0.000001. That is many orders of magnitude of reduction. Based on this case, I would say that the solution, of course, is converged because we have about 5 or 6 magnitudes of reduction of the residuals and errors. Now, if the eigenvalues of the system that is dependent on the solution are complex, on the right, using this particular technique, we see that instead of on a log linear plot, there's some sort of oscillations. This is the so-called non-monotonic reduction. So these are the types of plots you want to see in CFD. Ideally, over additional iterations, these lines would stop reducing in error. That is, as you increase the iteration maybe to 200 or 300, they would level out. That is, as the solver is making additional iterations, the solution is not improving because the error has become constant. If you see 5 to 6 orders of magnitude of reduction of error for all equations of motion, and the error or residual starts leveling out after it's been reduced by multiple orders of magnitude, then you can safely say that the solution is converged. Let's look at a few more examples for convergence. Here on the right, we have residual on the y-axis in the log scale, and the x-axis is iteration. And we've plotted different types of residual versus iteration for different types of solvers. The GS method maybe only decreases by 2 orders of magnitude for 200 iterations. Other solvers are completely off the chart for residual reduction, and they converge only within a few iterations. So you can see some solver choices, that is the way they're discretized and march towards a steady solution perhaps to reduce residual, converge much faster. So the choice of the solver and the way the solution is found is critical, especially if each iteration, you might imagine, costs roughly the amount of same computer time. In reality, some solvers cost much more computer time per iteration than others, but they might have much better convergence properties in that they are reducing the residual error much faster. Let's summarize what we've done in this class today. First, we talked about stability analysis of the so-called Fourier or von Neumann analysis for linear equations. We then extended that to, of course, nonlinear equations, and we showed one example of a linear heat equation and one example for a nonlinear simple set of ODEs. We then showed how, through this stability analysis, we can recover the definition of the CFL number. This is exactly what the CFL number development did originally. Then we looked at and defined once again the residual, that is the error of the equations of motion at any particular time step, or more appropriately in a steady solution of particular iteration. We showed the mathematical definitions of the L1 and L2 norm. Typically, L2 norm means the root mean square of the error of all the points within the grid. L1 is simply the magnitude of all the error, the summation of all the error and its magnitude. These are the most basic statistics for estimating and quantifying error in computational fluid dynamics. Remember, stability and consistency, which we defined in this class, imply convergence. This is so-called Lack's theorem. And remember, it is important to understand convergence in CFD. And we talked about practical ways of doing and measuring residual. You'll look at the residual plots in your homework sets in this class and get used to looking at residual and deciding if you have a converged solution. Remember, you can only imply convergence if you have a grid-independent study and you have stability and consistency, and your residual has become very small relative to the initial residual over a large number of iterations or time. Here, CFD, its stability, the residual, and L2 norm should be orders of magnitude smaller than their initial values. And visual inspection of the solution should also be performed. Not only should you have a converged solutions, but you should also look at the results visually, which we'll talk about how to do in the next one of the next modules of the class in visualization. You should understand that you could have a converged solution, and it may not be the solution that you desire. It could be an unphysical solution for a particular case. Now, only with experience and time will you be able to really be proficient in all these types of analysis for CFD. Next time, we'll be looking at algebraic systems of equations. These can be used mainly and developed for solving linearized partial differential equations or linear partial differential equations. They're also applied in nonlinear solvers for the so-called iterative loops on a per iteration basis. Thank you very much for your time today. I'm Professor Steve Miller.